This begins our lesson on Le Chatelier's principle. Le Chatelier, a French chemist, studied equilibrium in terms of upsetting it by causing what's called a stress. If a system at equilibrium undergoes a stress, that system wants to do the opposite of what you've done to it to alleviate the stress. In words, Le Chatelier's principle reads, if a stress is applied to a system at equilibrium, the position of the equilibrium will shift to reduce the stress. Whatever you do, the system does the opposite to get back to the equilibrium. A system at equilibrium can undergo 3 different types of stress. We'll talk about them one at a time. The first of the 3 will be changing concentrations of either the reactants or the products. When we change the amount, or let's say the concentration of the reactant or the product, that creates a stress on a system that is in equilibrium. Let's suppose in the first of our example that we add more product. Adding more product creates a stress on a system by increasing what we called the reaction quotient, Q. If products are made, product over reactant is indeed that equilibrium constant, and if we have too much product, the reaction quotient becomes larger. Well, if we have too much product, increasing its amount, the system wants to do the opposite of what we've done. It wants to use up the extra amount. Adding product is the stress, so the equilibrium wants to shift to use up the excess amount of the product. Increasing the concentration of a product causes it to move away, using up the product. When I say moves away from the product, it's going to point left. If I point away from the product, pointing towards the reactants, we're going to use up the extra amount. We'll shift the equilibrium to the left and again achieve the constant that we had before the stress. K is indeed a constant once that equilibrium moves around. So adding more product, we shift left. Add more product, you want to use it up. Point away to use up the product. Suppose in a second scenario of changing the amount of a reactant or product, suppose we remove, by some kind of competing reaction, suppose we remove a reactant. Removing a reactant makes, again, the reaction quotient Q become larger than K. We're dividing by a smaller number, Q becomes larger. Well, if you remove reactant, you want to do the opposite of removing. You want to make more. If you take some away, the opposite is to put more in. So it says if you remove reactant, the system will want to make more, so you point at it. Which direction of our equilibrium is going to point at the reactant side? Well, that'll be pointing left. Removing reactant causes the equilibrium to shift left. What about adding reactant? If we increase the concentrations of a reactant, the reaction quotient becomes smaller than the initial K constant. If you add reactant, the system wants to do the opposite. If you add more, the system wants to use up the excess amount and get it back to an equilibrium. To use up the extra amount of reactant added to the system, you point away from it, using it pointing away towards the product side. So what direction will use up the excess reactant? Shifting right. The equilibrium will shift right if we add reactant, and the reactant quotient comes back to the first initial value. In the last scenario, what if we remove product? If we cause a stress by removing product, the system wants to do the exact opposite of what we've done. Removing product is the stress. The exact opposite is add more. How do we add more product? Well, the system will shift right to create more product to alleviate the stress we've put on the system. Simply by determining the effect on Q, that reaction quotient, it will help us determine if we're going to shift left or shift right. So repeating, add product, you want to use up the product, shift left. If you remove reactant, you want more reactant, shift left. If you add reactant, the opposite of adding is using it up, point away from it, shift right. Removing product, well, the opposite of removing is to put more in, point at it to make more, it will shift right. The first of the three stresses is changing the concentrations by either adding reactant or product or removing reactant or product in terms of molar concentration. Whatever you do to the system does the exact opposite to alleviate the stress. Remember Le Chatelier's principle. If a stress is applied to a system that's at equilibrium, the equilibrium will simply shift to relieve the stress. What you do, the system will counteract by doing the exact opposite. Let's give it some thought. Here's an equilibrium. We have 2 moles of gaseous nitrous oxide reacting with 1 mole of gaseous oxygen in dynamic equilibrium with 2 gaseous moles of nitrogen dioxide. What would happen to this equilibrium if oxygen is added to the system? What do we do to the equilibrium if NO is removed? Well, let's consider that first scenario. Let's put a stress on the system. Let's add oxygen. Notice where oxygen is? It's a reactant. If I create a stress by adding more oxygen, the system is going to counteract that by doing the exact opposite of what we've done. What's the opposite of adding oxygen? Removing it. If I want to remove oxygen from this system in equilibrium, I want to use it up, I better point away. When I say point away, the arrow literally points away from the oxygen towards the product side. What if NO is removed? Let's put a stress on the system where NO is removed. NO is a reactant. What's the opposite of removing NO? Well, making more. If I want to make more NO, which direction would our arrow point? Put your answers down. Take a guess. Did you say that adding oxygen will shift the equilibrium to the right? Remembering, adding oxygen's the stress, so the system wants to relieve that stress by using up the extra amount. Point away from the oxygen, reactant toward the product. That's what I mean when I say shift right. Pointing to the right uses oxygen to use up the extra amount. If NO was removed, we said removing NO as a stress, that the system would counteract that by wanting to make more. Which direction will make more nitrous oxide? Well, shifting to the left. The arrow that points left, the reverse reaction, is going to make more NO. We would say that the system would shift left. We'll turn our notepad page. A second stress could be in a gaseous equilibrium, changing the pressure. Now, the first was changing molar concentrations. The second of our 3 stresses is changing pressure. Now, if we have a system that's all gaseous, like gaseous reactants forming gaseous moles, we can manipulate pressure changes by simply reducing or increasing. But here we'll look at the first scenario. Let's reduce volume. Now, by reducing volume, according to Boyle's law, you can actually increase the pressure. We've studied the gas laws well enough to know that P's and V's, pressures and volumes, are inversely related. If I reduce the size of the container, we'll have more collisions in those gaseous molecules, creating a greater pressure. If I put the reaction in a larger container, increase the volume, those molecules won't hit as often, therefore the pressure would drop. I manipulate pressure by volume changes, P's and V's being inversely related. If I reduce the volume, pressure increases. If I increase the volume, pressure will drop. Now that's kind of background knowledge to see what would happen as we change the pressure of a system in equilibrium. And let's consider just an example. Again, more margin notes to help us understand pressure changes. It says gas pressure is created by particles literally hitting the side of the container. The more and more particles, the greater pressure. Anything I can do to increase collisions is going to increase the pressure, and vice versa. So let's look at a scenario for a familiar equation, the production of ammonia. We have one gaseous molecule of nitrogen with three gaseous molecules of hydrogen in dynamic equilibrium with 2 gaseous moles of ammonia. Count up how many gaseous moles you see on the left side of the arrow. Well, I see 1 nitrogen, 3 hydrogen, so 4 gaseous moles. On the right side, I only see 2 gaseous moles. 4 versus 2. Pressure is sheer numbers of particles. So looking at the left side, since it has more gaseous moles than the right side, it would create more pressure. So if the left side of the arrow is being favored, that's higher pressure compared to the right side of the arrow, which would be lower pressure. So by manipulating volume, we can cause equilibriums to shift by favoring systems with greater or fewer gaseous moles. Let's suppose we reduce the volume. That's the same thing as saying increasing the pressure. So when something says we reduce the volume, it's really telling you the stress is increased pressure. The system wants to counteract that. The system will do exactly the opposite of what you've done. What's the opposite of increasing? Well, that's decreasing pressure. So the system will move to the least gaseous moles. Which direction would it move to achieve the least gaseous moles? And so we simply count up and find the side with the fewer gaseous moles, and that's the side that the equilibrium would then favor. Manipulating volume truly is the same as saying manipulation of pressure. And the way that we can determine which side of the equilibrium will be favored is just simply by counting up the moles. Now, a second way to manipulate pressure is by adding what's called an inert gas. An inert gas, the same as saying a non-reactive gas, changes the pressure of both the reactants and products there in terms of total pressure in the system, but yet since it's not part of the equilibrium, it really has no effect on the equilibrium position. If I'm studying a system in equilibrium and I add a gas that's totally unrelated to the system that I'm studying, it's known as an inert, does not react. For example, the noble gases, those found in the far right of our column 8A, helium, neon, argon, krypton, xenon, radon, those are known as the inert or the noble gases. I can put another gas inside the chamber and actually raise the pressure, but since it's not part of our equilibrium, it absolutely has no effect on the equilibrium. So often those are little tricks that the AP exam could put on there. You'll see adding pressure by adding a xenon molecule or a neon molecule. Don't fall for that. Adding pressure with an inert gas, a non-reactive gas, does not cause a change in equilibrium. So let's look at this example and see what we think. Here we have 2 gaseous moles of sulfur dioxide with 1 gaseous mole of oxygen in dynamic equilibrium with 2 gaseous moles of sulfur trioxide. I have a total of 3 gaseous moles to the left on the reactant side and 2 gaseous moles on the right. We call that the product side. So what would happen to the equilibrium if the volume of the system increased? Let's consider that first. Kind of talk through a strategy here. If volume is increased, what are they really telling you the stress is? What happens to pressure if you increase volume? We know Boyle's law, P's and V's are inversely related. Increasing pressure, oh, that's the same as saying dropping the pressure. If I drop the pressure, that's the stress. The stress is low pressure, so the system wants to do the opposite. The opposite of dropping pressure is to make more pressure. Which side of the arrow? Would you point at left or would you point right to make more pressure? Suppose argon is added to the reaction vessel, causing an increase in the total pressure. Would that affect the equilibrium? What do you think? Well, let's change slide and let's see what you've written down. If the volume of the system increased as we had just discussed, we had said increasing volume is the same as saying decreasing pressure. So we realize, according to Boyle's law, decreased pressure is the stress. That system wants to do the opposite of what we've done. Well, the opposite of dropping pressure is to create more pressure. Which side of our arrow has more gaseous moles? Well, the left side does. Therefore, the equilibrium will shift left. When I shift left, I create more gaseous moles, and therefore I'll have more collisions, and the pressure will again increase. Adding argon, we decided argon is not part of the reactants or products up above in this dynamic equilibrium. It will change the pressure inside the container, but it won't play a role in the equilibrium. Therefore, there'll be no effect on the equilibrium. It will not shift in either direction with the addition of an inert gas. We've talked about number 1, changing concentrations of reactants and products as a first type of stress in Le Chatelier. Second type, we've talked about pressure changes. If we change the pressure, we change the volume or vice versa. The third type of stress in Le Chatelier is called a change in temperature, adding heat or removing heat from a system. Now, a couple of things from our kinetics chapter also plays a role. We understand that changes in temperature affect the rate of both the forward and the reverse reaction. Kinetics is studied in knowing that it affects the rate. It doesn't just change the equilibrium position, but it also changes the equilibrium constant, and that we had studied looking at the Arrhenius equation. We can calculate activation energy by varying the temperatures and studying the rate constants. Now, in terms of Le Chatelier and equilibrium, we look at the temperature changes really as being an effect of whether or not a reaction is exothermic, heat releasing, or endothermic, heat absorbing. Simply looking at whether or not a system that is in endo or exothermic lets us decide really if heat is being absorbed or if heat is being released, and we can treat it really as nothing more than another reactant or product. Let's take one scenario at a time to help that lesson get reinforced. Let's suppose we have an exothermic reaction where the enthalpy, that's delta H, I often think of that just really as the heat of the reaction. If enthalpy is less than 0, that's just the way I wrote down that enthalpy is negative. We have a negative delta H. We know that that's heat releasing. That's the very definition of exothermic reactions. But what does that mean? If exothermic, heat released, you can think of heat measured in kilojoules as nothing more than a product. And if it's a product, we can really treat it as any other product, and we change the concentrations from our first stress. Let's think about heat as a product, and we raise the temperature, adding heat to a system. Well, what's the opposite of raising temperature? Or if I could say, what's the opposite of adding heat? Well, lowering heat is the opposite. And if I want to lower heat, I have to use it up. And to use up heat that's on the product side, I got to point away. Pointing from the right towards the left uses excess heat. If I add heat to a system that is exothermic, that will cause the equilibrium to shift left. Shifting left uses up the excess heat. Increasing heat is the stress. I want to point away from the heat to reduce the heat, to use it up, get it back to equilibrium value, shift to the left. And the opposite is true as well. If I lower the heat of an exothermic reaction, removing heat, I want to point at it to make more. Well, which direction points at heat? Well, pointing to the right of our equation points at the word heat. It will shift to the right if you lower heat. So just placing that exothermic heat value on the product side lets us move away from it or point at it if we want more or less. What about endothermic values? Well, endothermic values are positive delta H's. When we think about heat being absorbed, delta H, the enthalpy of a reaction, we could also think of that as just the heat of a reaction, would have a positive sign. Heat is being absorbed. If heat is needed or needs to be input, we think of it as a reactant. Absorbing heat means heat is required for the reaction to get going. Think of it as a reactant. Exothermic product, endothermic reactant. Exothermic comes out, endothermic goes in. If we raise the temperature of an endothermic reaction, thinking heat as a reactant, if I add heat, what's the opposite of adding heat? Well, using it, right? Get rid of the excess heat. Point away from the heat to use it up. This equilibrium will shift to the right. If I add heat, it says raising the temperature. If I raise the temperature, the stress is more heat. Point away from it to use it up to get this system back to equilibrium. Oh, I see a typo on this slide. Heat plus A plus B is in dynamic equilibrium with C and D. Too many equal signs, I apologize. Heat plus A plus B treats the two reactants A and B with heat. Now opposite, what if we remove heat on an endothermic? If we create a stress of lowering the temperature, well, we want to make more. Point at it. The equilibrium shifts to the left to make more heat. Systems that are in dynamic equilibrium want to do whatever it takes to get back to the original happiness of equilibrium. If you create a stress, it's going to do the opposite. If we raise the heat, you want to point away from the heat to reduce it. The shift is to the right. How about this? Dinitrogen tetraoxide, N2O4, in dynamic equilibrium with 2 gaseous moles of nitrogen dioxide. Look at the positive delta endothermic value, positive 58 kJs. Which direction would the equilibrium shift if I add more N2O4? If I add N2O4, which direction will it shift? What do you think? Write it down. Don't wait for me. Write it down. Add more N2O4. What direction did it shift? Well, did you say to the right? If you add more N2O4, what's the opposite of more? Less. If I want to get less, I got to use it up. Using it makes it a reactant. Point away to use it up. Pointing away means I want to start left and point to the right. Shifting away from the N2O4 points to the right, and I can decrease that amount again and get back to the original state of equilibrium. Adding more N2O4 causes the equilibrium to shift to the right. What if, same equilibrium, what if we remove NO2? See where NO2 is on our equilibrium? It's on the product side. What if we remove some? Which direction would it shift? Write your answer down. Did you say that removing NO2 would cause the equilibrium to shift to the right? If we remove NO2, the system's going to do the opposite. The opposite of removing it is to make more. So you point at it. Pointing to the right, the equilibrium arrow points to the right and we'll make more. Removing a product causes the equilibrium to shift to the right. What about the total pressure being increased by adding nitrogen gas? What happens to the equilibrium if we add nitrogen? Jot it down. Did you say that it will have no effect? Equilibrium is not changed by the addition of the inert gas. N2 is not part of the equilibrium we're studying. N2O4 in dynamic equilibrium with NO2. I don't see the nitrogen anywhere. It will have no effect on the equilibrium. Don't fall for those little trick ones. I've seen them turn up on the AP exam. Same equilibrium. What would happen to the equilibrium if the volume is increased? We might have to flip your notepad page to keep going. If the volume's increased, well, let's count. Volume increase. What does that really mean? Well, the stress means, okay, opposite of increase. P's and V's inversely related. If V goes up, P goes down. So the stress is pressure dropping. The opposite of low pressure is greater pressure. Which direction will the equilibrium shift to create more pressure, the opposite of what the stress is? Did you say shift right? We know that the Boyle's law relationship says that increasing volume drops our pressure. The stress is to lower pressure, so the system wants to do the opposite, and it wants to make more pressure. Which side had more gaseous moles? The right side. This equilibrium shifts to the right. And one more consideration. We see that this delta H value is endothermic. What happens if we lower the temperature? What would the system do to an endothermic reaction if I drop the temperature? Well, let's see. Endothermic. Heat is required. If heat is required, do I place it on the reactant side or the product side? Glance back and see what we said. What happens to the temperature? Jot down your answer. Well, I know that that reaction was endothermic. As soon as I saw that positive on the delta H, the enthalpy of reaction is endothermic. So now I know to think of that heat as a reactant, right up there with N2O4 plus heat. If I drop the temperature, that's the stress, decreasing temperature, that system wants to do the opposite. It wants to make more heat. I got to point at it. I got to point to make more heat. If I drop the temperature, oh, I wrote shift right. Temperature is decreased, it's going to shift left. When I shift left, I can make more heat. Please make a note on your notepad page. Don't write down what I mistakenly wrote down. I apologize, but you're going to change it for me. It's going to shift left to make more heat. Decreasing the temperature of an endothermic reaction, we want to point at the heat. Well, if the heat's on the left, I better point left to make more heat. This is an opportunity to pull in some thermodynamics, and I've seen this done quite often on the AP exam, trying to integrate as many topics as they can into one essay or one free response answer. We're going to pull out the Appendix C of our chemistry book, and you may have one photocopied yet from last year or earlier in this year. Appendix C has the thermochemical quantities, and you'll see the an alphabetical listing and delta H values. There's some other things, delta G, Gibbs free energy, delta S, the entropy. We've most often used that Appendix C for the enthalpy values, delta H. They're called the standard heats of formation. You will need your Appendix C to do some of these homework problems. Now, if you have a photocopied version, great. Otherwise, you're going to have to open the back of your chemistry book and find the Appendix C. Now, I've done some of this for you in this PowerPoint lecture, but realize when it comes time to work your own problems, you'll need access to find these numbers. When we use the standard heat of formation data in Appendix C, we can determine the standard enthalpy change for the reaction. Okay, so here's code for what that's saying. Previous slides, I said, here's an equation, here's delta H, and I said it's positive or negative, such and such. This is an opportunity to make you work for it. And again, it's just an opportunity to integrate a little concept on heats of formation and Hess's law from a previous chapter, and the AP exam is great at doing that. Let's determine how the equilibrium would be changed, or shift left, shift right, with temperature changes. But in order to do that, we've got to find whether or not this reaction is endo or exothermic. And so this is where we go to work, finding the values in our Appendix C. Now, a good margin note here. To find a heat of a reaction, recall this is our formula. The sum, see that sigma? That's a Greek symbol that represents the sum. The sum of the products minus the sum of the reactants. Products minus reactants, where coefficients are distributed through the values we find in Appendix C. You'll need your book to find these values, or perhaps you can pull out a photocopied version from your folder somewhere, but you definitely need access to do these problems. Now, I did this for you. I went to the back of the book and I pulled up these values. I found the delta H of formation for ammonia, NH3. It's alphabetical, so look into the N's and find NH3 in the gaseous form. It reads negative 46.19 kilojoules. Now, the very definition of heats of formation says any element in its natural state is going to have a formation value of 0. We don't form elements. Those are things that we build compounds from. So it makes sense that hydrogen and nitrogen, which in their molecular state, the way we find them in nature, are assigned a value of 0. So the original equation, nitrogen plus 3 hydrogens in dynamic equilibrium with 2 ammonias. I want to know the delta H value, products minus reactants. Well, there's 2 gaseous moles of ammonia, so I distribute 2 through the negative 46.19, and I find the total value of product minus the total value of our reactant, a sum of 0. So I find delta H being an exothermic value. So products minus reactants are just making us do a little legwork to find the delta H. Knowing as soon as it's negative, I identify that as exothermic. Exothermic treats heat as a product. It's releasing from the system. If I increase heat, I'll shift left to use up the heat. If I decrease heat, I'm going to shift to the right to make more heat. Do the opposite of the stress. This little twist in the lesson is truly nothing more than a review of enthalpy, heats of reaction, where we use our formula products minus reactants. Once we have the sign on the delta H, we can quickly determine which way the symbol, or which way the heat will be placed, on the left side or the right side of the equilibrium, and therefore determine if we have a shift left or shift right. Another opportunity to try one. Using our Appendix C, says this example, determine the enthalpy change for the following reaction. 2 gaseous moles of POCl3 in dynamic equilibrium with 2 gaseous moles of PCl3 and 1 gaseous mole of oxygen. Pull out your Appendix C and one at a time find their values. Well, I know oxygen, molecular form of oxygen, found in its natural state, that's going to be a 0. But in the P's, it's an alphabetical listing in Appendix C. What do you find for the other 2? Take the sum of the product minus the sum of the reactants and calculate the delta H for your reaction. Pause the video, do that math, and start up again when ready. I'm just trying to encourage you to practice with me so that when you get to the homework problems, you'll have that feedback that you need. All right, so now you've looked up those values. We see that the product, PCl3, had a value of negative 288.07. That's the product, and there were 2 moles worth of it, so I distribute a 2. The plus 0 reminds us that molecular oxygen had a value of 0. The sum of the product minus the sum of the reactant. Did you find gaseous POCl3? It had a value of negative 542.2 kilojoules. The sum of the product minus the sum of reactant gave us a positive overall delta H. As soon as I notice a positive sign, I know to treat it as an endothermic reactant, placing it on the left side of our arrow. So if you add heat, it'll shift to the right to use up the extra heat. If we remove heat, it's going to shift to the left to make more heat. A little delta H calculation, product minus reactant, where once we determine the sign, it just goes back to deciding how that would cause the equilibrium to shift in terms of reactant or product. The last little concept is the use of catalysts. Catalysts are a lot like inert gases, placed into equilibrium problems really to try to cause you grief. Catalysts, I know, increase the rate of a chemical reaction, but once equilibrium is achieved, catalysts have no effect. Think about affecting the forward and the reverse reaction in the same condition. It doesn't change the equilibrium position. It will change how fast a system gets to equilibrium, but once it's achieved, adding a catalyst to a system will not change the amount of reactant or the amount of product present. So if you see something that says, adding a catalyst to an equilibrium, how will that cause it to shift? And your answer is, no effect. Just as if they had said, adding some inert gas, how would that cause the equilibrium to shift? And you'd say, no effect. So catalysts do not affect the equilibrium. Where you've gotten now is a great place to pause the video. We'll come back together in class time and put the concepts together. But you have enough ammunition now to do quite well on lesson number 4, called Le Chatelier's Principle, applying today's topic. And I'd like you to begin lesson number 5, additional exercises. Complete lesson 4 and lesson 5 to the best of your ability and come with any questions you might have for class time and we can tackle them then.